I just want to give you a feel for a cipher, which is a nice example here, that is weaker than you would expect. And this is supposed to motivate why we use nonlinearity in ciphers. So I'm calling it, this is being called the linear cipher. So you have vectors as your block of information, which is standard in block ciphers anyway. And then your key is actually a matrix, and your encryption mapping is matrix multiplication. Okay? And if you want, your key might have a matrix multiplication plus an unknown addition, a more general linear mapping. Okay? So what we would like to understand right here, and I will switch to the blank page that I have and try and explain this a little bit, is why is this weak? So this is just an overview of what analysis might look like, and we would think about it in various terms. And as all of you know, for any kind of practical analysis, we have some assumptions. So for example, you would have learned this before in crypto. There is known plain text, chosen plain text, etc. Let's just assume known plain text. So the point is, to break a cipher, okay, no modern cipher, maybe this one is weak, but in general, no strong modern cipher can be broken by ciphertext only, unless there has been a catastrophic failure, okay? That happened in World War II with Enigma, but that's because those encryption mechanisms, which were equivalent to current day stream ciphers in some sense, they use natural language. And natural language is not, as you know, different letters often occur with different probabilities. So that gives you a way into cracking things. But in modern cryptography, we have to assume, because we would use compression. We would compress the information so that it would be uniform. We have to assume plain texts are uniform, keys are uniform, randomly chosen, so the ciphertext is uniform. So the attacker does need, by Kerckhoffs's principle, the attacker knows the design of the cipher. He doesn't know the key, and he can have an access to small number of plain texts and the corresponding ciphertexts under the unknown key. So what he needs to do, or she, is can he determine the key, given this? So let's see how you might do that. So now I've actually prepared some blank pages so I can type, because the iPad just wasn't working. Okay, oops. Okay, the small cipher. All right, so I'll start here. So basically what we need to do is so given, other thing I hate is this thing always goes to a tiny setting regardless of what I do. I don't want it purple. Let's just have black. Blue is not bad. So given that we know a set of plain texts, say P1, P2, P8, let's say we have 8 plain texts and corresponding ciphertexts. C1, C8. we want to find the unknown key. Okay. Okay, so let me just format this a little bit. Okay, so I told you the mapping. The mapping was that ciphertext equals K times plain text. This is, sorry for this won't be the most readable typesetting thing, but it's matrix multiplication. But we're assuming block length is n equals 8, so it's an 8 by 8 matrix. K is randomly chosen unknown key. We want to solve for K. And the question is, can we do that efficiently? Does anybody have any ideas about, given your knowledge of matrix algebra or whatever from before, how you might do this? And of course, the question is going to be, can you do this efficiently? We're looking at a small case of block length 8 bits, but in general, this could be much larger. Do we have any ideas at all? Okay, what do I know? I know Ci is K times Pi. I equals 1, 2, all the way to 8. How do I know this? Because I've been told. The attacker is given plain text and corresponding ciphertext encrypted under the unknown key K, and the unknown key K is this matrix. Is that clear? So I know this. Okay, excellent. How can I make use of this knowledge? Let me define a big matrix C made up of these columns. So put all the ciphertext together, side by side. This is now an 8 by 8 matrix. Put the corresponding plain text together, side by side. Oops. Does everybody understand how you do a block matrix? You just write the columns next to each other and you end up with an 8 by 8 matrix. In the actual matrix, there are no vertical lines. It's just a way of indicating that's what I've done. Okay? Now, each Ci is K times Pi. And since you've ordered them in the same way, this means that we know that the matrix C is K times the matrix P. Because that's how matrix multiplication works, right? Everyone okay with this? Excellent. So, how can I solve for K? I have a matrix equation. Invert. Yes. Okay. Excellent. Yeah. Okay, let me see. actually. I don't want to waste the whole space. So I'll be doing this kind of post typesetting all the time. I'm sorry. Make maximum use of the space. So therefore I can write K equals, and again, the mathematical notation is not so nice, but it's basically P, actual K equals, let's just say, inverse P times C. Is that correct? It's incorrect. Matrix multiplication is not commutative. So actually, let us remind you of that. So I have C multiplied by inverse P. Hang on, please. Let me finish this and we'll talk. C inverse P, K P inverse P. I multiply on right by inverse of P matrix. That means C inverse P is K times that becomes identity is K. You gotta be careful with matrices because I just wrote, okay, inverse PK, but it's not true. Now, go ahead. You can either type the question or ask. Was it a mistake or I've answered what you were going to say? So I can get the K this way. Now, this would be fine if n equals to 8. So fine for n equals 8. How complicated is it? How computationally difficult is it to invert a matrix? It's not as easy as you think. Or you may know, if you've done linear algebra, you do this Gaussian elimination, canceling rows and going backwards and so on. So complexity of matrix inversion. This is an open problem, as in we don't know the exact number, but we have an upper estimate. We don't know if there's anything better in general. But we know for an n by n matrix, the inverse takes, if you do the silly way, you know, the high school way where they tell you apply that, divide by the determinant and apply all those adjugate mappings, that would be O n cubed, but the best known is like 2.4 something. It's more than quadratic in the size of n. So for large n, this is prohibitive. Oh, you're absolutely right. This is the obvious way to do it, but the obvious way to do it is too inefficient. Does everybody remember O notation? O n to something means a constant times n to that. We don't really care about the constant, we care about the growth rate. So if n is 128, this is 128 to the 2.4. Again, it's not too bad. In practice, you wouldn't use that out there. Why? Because, I mean, the bloody thing is linear. That's why. Even the stupid method for real world parameters, yeah, you can throw some computing at it. But the point is not that. The point is there is a much faster way. Okay, given the time, maybe I take a 10-minute break now and I'll tell you after what the quick way is, and then we'll move on to the next part of the slides. in papers, it's called omega. Everybody has decided to call it omega because nobody wants to write down 2 point, I don't know what it is, 403, blah, 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 blah. Doesn't really matter. Okay, excellent. So how can we find this k faster? Let's, okay. All right. Let's move to the next page. And I need to set it to edit again. There is actually a functionality called whiteboard on Canvas, but last year I found that it was timing out and doing weird stuff, so I don't want to take the risk. Okay. Now, matrix, it goes back. Everybody knows this, right? The most general linear mapping between vectors is represented by a matrix. That means M times, I don't put the dot, P1 plus P2 equals what? MP1 plus MP2. That's the meaning of linear, right? Output of the sum, the function applied to the sum of input points is the sum of the individual functions, individual points being applied the same function, right? We can use this and we can actually crack this cipher much more quickly. Just think of it this way. So for convenience, I will write row vectors. This is the other thing. It decides, it knows how wide I want it. I will write row vectors with transpose. So let's say my P is, okay, this is going to be, because I called it PI first. Okay, PI1, comma, PI2, PIN. So has n components. I told you I was going to write the transpose because it's actually a vertical vector. Doesn't really matter for us. Do you remember what a basis is? A basis in vector space is a way of writing the vector as a linear combination of some basic vectors. So basis. So for example, I get 8. 1, 2, 3, 4, 5, 6, 7, 8. So let me just copy it over. I'll fix it. So put a 1 in the first component, put a 1 in the second component, and in the end, put a 1 in the last component. So therefore, I can write EI equals, I'll call this set, ordered set E1 to E8 in this case. So it's an ordered set. Pi is Pi1 times E1 plus Pi2 times E2. So tiny example, if you're not sure. If I have, it doesn't have to be binary. Let me do non-binary because It holds in general. 1 times, it's like a coordinate. 2 times plus minus 1 times plus 4 times. Expand any vector in terms of the coordinates multiplied by the correct basis. So that's scalar multiplication. So the whole point is I can decompose my P this way. And because the mapping is linear, constant P equals C in P where C is a scalar. We have binary, so only scalars are 0 and 1. But that's fine. But it's even simpler in binary. It's true in general, but it's simpler in binary. So here's the point. So if I can do chosen plain text, encrypt 1, 0, 0, encrypt E1, E2, E8 at V1, V2, V8 via sorry about this. We'll get there. So basically, VI is MK. VI. Did I switch to M from, did I call it K before? Oh, yeah, I should use K because I had K for the key. Excuse me. So for each basis vector, I find what the output is and call it VI. Need only N, 8 operations for this. Then I know K I is P I1 V1 plus PI2 V2 because the mapping is linear. PI8 V8. So as soon as I know what it is for the EIs, I can calculate what it is for an arbitrary P because I can decompose the P in terms of the coordinates into this sum, and I apply K to this sum. And then these are scalars, I take them to the left because of this, and sum and get them. So the whole point is, because also I'm doing binary, if there is a 0 bit, the output will be 0. So I don't even have to compute. If PI is 0, that contribution is 0. So I just need to look at the I's, where the input bit is non-zero, find the corresponding V vector, and then add them up. Linearity is the enemy of security, and this is why there's all that theory about nonlinearity. So linearity is a weakness which we eliminate in modern ciphers, let's say, because it's true for everything. Okay, so affine, linear, it could be affine as well. That would make no difference. If I add a constant, I'll just add the constant at the end. Okay. me just save that. So I will obviously upload this as well. So let's go back. So he says basically the same thing. Key size is not sufficient. Purely linear is bad. So you know these attacks from before.